So we have been looking at various topologies on spaces, and there are some general principles which tell you very correct, natural ways to construct topologies. We did for specific examples, and these are initial and final topologies. More generally, you have the notion of initial and final topological spaces, which we will see later, where even the set is to be determined, but with initial and final topologies, we have a space and we want to define the correct topology on it based on some functions on that space. Okay, so let me first we need to define a auxiliary notion, that of being coarser or final. Okay, so let X be a set, and for once it's not going to be a topological space because we want two topologies on it. So let omega 1, omega 2 be topologies. So they are collections of sets, subsets, which satisfy the correct properties. Okay, so suppose if omega 1 is contained in omega 2, we say, so that means omega 1 has fewer sets than omega 2. Omega 2 can resolve things better. We say omega 1 is coarser than omega 2, and omega 2 is finer than omega 1. So having more open sets. So the other terms that are used here are weaker and stronger. As you'll see, this is kind of confusing, the terms. Coarser and finer at least makes it so you can imagine what they mean. It's because the role of the topology and the domain and codomain are in some sense opposite, as we will see in the some extent in the examples in a few minutes. So which is stronger and which is weaker depends on whether you're thinking of them as topologies on the domain or on the codomain. So here the term is actually correct if you're thinking of them as a domain and codomain. So let's just note, for example, that for on any set X, on any X, the discrete topology, well, it contains as many open sets as you can. So discrete topology is the finest. And of course you will guess, and the indiscrete the coarsest. And this is useful to note. But by itself this is not so interesting. What is more interesting is when we constrain the topology. So here is an example. So recall, of course, that if A is contained, so if X is a topological space, and A is contained in X, subset has subspace topology. Let me call this omega A from X maybe, with the subspace topology is exactly the intersections of V intersection A, V contained in X open. Okay, and we know that I from A to X is continuous. Let's recall the proof of this as V contained in X open. If V is open, this implies that I inverse of V, which is V intersection A, is open. So you notice immediately I being open is telling you that these sets must be open, and the subspace topology is defined by saying only these sets must be open. So that is exactly what the following statement says. Proposition is that the subspace topology is the coarsest topology not unconditionally, such that I on A, of course, such that I from A to X is continuous. So we have a function on A and we have topology, and it's characterized by being the coarsest topology, so that that function is continuous. Okay, we can't talk about the finest topology such that it's continuous, or rather no, there's no logical problem talking about it, but it's highly uninteresting because the discrete topology makes everything continuous. So the finest topology, so that some function is continuous, is always the discrete topology. But coarsest is how few open sets you need, and that has some content, because for instance with the indiscrete topologies hardly any function is continuous, as you see. So we can't just take something arbitrarily coarse and expect these functions to be continuous. Okay, so let's look at proof of that. Well, there's only a matter of notation. It's very simple. So let omega be a topology on A such that I is continuous. Okay, so we have to show that this is coarser than omega. Okay, so what hence, well, we just saw earlier, so V is contained in X open implies that I inverse of A, so that is going to be V intersection A, this is just I inverse of V, is open. Okay, so thus if I take any set V intersection A in, or rather let me not be so lazy, let's take thus W in omega AX implies that W is V intersection A where V in X is open. This implies is open that in A omega, that is V intersection A is contained in omega. Okay, so that's what we wanted to clarify. Okay, so if omega be another topology on A and V intersection A is contained in omega, so if we have any set which is open in the subspace topology, it's of this form, and we have already concluded that that implies that W, which is V intersection A, is contained in omega. Okay, that's it. So any set in this topology is contained in this topology. So that is, if you wish, omega AX is contained in omega. Okay, this is the situation in which we will say that the subspace topology, which is the coarsest topology so that this function is continuous, is the initial topology given by these functions. So it's the initial topology, initial because it's on the initial object, the domain, and it would be final if it was on the final object, which we will come to in a minute. But let's just note, so in general, given a space, let's say get Z and functions, well, in this case we had just one, but in general we could have a collection F alpha from Z to, well, they could also go to lots of spaces. Okay, so alpha in A, so we are given this, Y alpha are topological spaces. So we have functions and the target topology is unknown. We say, sorry, so the initial topology generated by Z is the coarsest topology. Topology on Z such that F alpha is continuous for all alpha. Now there's a question that you must ask, which is, well, coarseness of topology is set containment. That's a partial order, not a total order. Why should there be a coarsest topology? Why should there be a minimum? In a total order also you may not have a minimum, you may have supremum or something, but in a partial order certainly not. So I mean, this is an issue. But then the thing is that we can intersections of topologies are topologies. So proposition, the initial topology always exists. exists. Okay. So this is again a general principle. How would you construct such an initial topology? Well, just observe that if omega and omega prime are topologies, or it need not be just a pair, okay. So I'll just write it in a general term. The intersection of topologies is a topology. This is a good exercise. Remember, we had 3 properties of topologies. That is, the third was containing the open phi and the whole space. The first was closed under unions, and the second was closed under finite intersections. And you'll see that if I take a collection of topologies and I have a sets which are closed, which are open in all of them, then the union is open in all of them and hence contained in the intersection of the topologies. And the same goes with finite intersections and so on. Okay, and if f alpha is continuous in a family of topologies, or with respect to a family of topologies, it is continuous in all of them. So, initial topology is the intersection of all omega such that omega is a topology on Z, and f alpha from Z omega to y alpha is continuous for all alpha. So I've taken an intersection of sets of topologies, and intersection of these will also be a topology. Clearly, any topology which satisfies the conditions is contained in this set, so it contains the intersection. The last point is, how do we know this is non-empty? Well, we know this is non-empty because the discrete topology, everything is continuous. So we at least have one topology here, and so this gives you the coarsest topology which has these things. Okay, so we always have an initial topology, and our specific example that we had was the case of subspace topology. So often you have a, so the broad principle is that we have a set and we want to put a topology on it. And as I said, topology is the setting for continuous functions. So we decide which functions we need to be continuous on it. Decide meaning what made us construct the topological space usually tells us what functions we need to be continuous on it, and then take the coarsest topology. This works extremely well, and for sophisticated constructions like the product, we will find these things. On the here's another example. On the other hand, for other cases, we will need instead the final topology, which I'll come to in a moment with one example. But first, another example for this is that if XD is a metric space, the metric topology. Well, what functions do we have from a metric space? Metric topology is the initial topology with distance is continuous. Let me write that here. So here we have distance between P and some function continuous. Okay, maybe a dot is better notation. So for any fixed P, we have the distance from P. All these are continuous functions as we have seen, and we take the initial topology so that all these are continuous. The coarsest one, we get indeed the metric topology. This is very easy to see because we get the balls by construction from this, from the continuity, and we know that they form a basis. And so the unions will also have to be in this kind of topology. Okay, so the last thing we will see in this video is the final topology. The final topology is where we have things in the other direction. So instead of being given, we are given a space again, or rather a set. Okay, so we are given, let me again call it Z, let's say, and set. And this time we are given a bunch of functions into the set, y alpha to z, where y alpha is a topological space. So we have this set, y alpha topological space. And then the final topology. So everything is dual in a sense, so we have to reverse everything. The inclusions go the other way. So the final topology on Z, this time being, instead of being the coarsest, is the finest topology. On Z, such that each f alpha is continuous. Again, if I took the other case, which is coarsest, it would be useless because the indiscrete topology makes everything continuous. So the answer to the coarsest, and which is not useful, is that you have to take this the indiscrete topology. But on the other hand, finest topology means is something non-trivial. So proposition, the final topology exists. And the proof is exactly the same as before. That is, you take the, it's not exactly the same, because now you want to make things bigger. Proof, take now not the biggest, smallest, union of topologies with each f alpha continuous. And again, the union of continuous topological spaces is going to, union of topologies is going to be a topology. And if f alpha is continuous with respect to all of them, it is clearly continuous with respect to the union, because any open set is open in one of them. Okay, so you can see the way these things work in dual. So if we generally have a function from x to y, so the inverse images of open sets here are required to be open sets here. So having more open sets here strengthens this condition, and having more open sets here weakens it, meaning makes it makes the chance it's satisfied greater. So you would like to take as few open sets here as required to make something continuous, or as many open sets as permitting certain functions to be continuous. It's the dual nature of these things. It's because of the condition that for all open sets in the codomain we need a condition on the domain, subsets of the domain. Okay, so here is a quick example. Suppose we have x is the disjoint union alpha in A of x alpha, and that is, I'll take a simpler meaning of this thing's x is union of x alpha, alpha in A, and x alpha intersection x beta is empty for all alpha beta in A, and this is as sets. So suppose this is again dual to our subspace, except that here we have more data. So there in the subspace we had a space and we wanted to put a topology on the subspace. Now we have a set which is consisting of lots of spaces, and we are given topologies on x alpha. If you wish, you can call them omega alpha. As usual, they'll be suppressed from the notation on x alpha. Okay. Then the disjoint union topology. Now this is going to be the final topology. Such that, well, the set of all inclusion maps I alpha from x alpha to x is continuous for all alpha. Okay, and that means that if a set V is open here, so suppose I have here x, suppose I have a set V that is open here, its inverse image must be open, so its intersection with each x alphas will have to be open. Okay, and finest topology means, so this will tell you that V has to have the condition that its intersection with each V alpha, X alpha is open. This is also true if I took the indiscrete topology in a rather silly way. But because we are taking the finest one, we impose the converse. Okay, you can't always do it because you might need to take unions and closures, but concretely in this case you can simply describe it. So V contained in X open if and only if V intersection X alpha is open for all alpha in A. Okay, so this is a topology, it's easy to see, and then hence it is the final topology. Okay, just as I said, the warning. So the condition of these I alphas being open tells you that if V is open, V intersection X alpha is open. We put the other arrow. In the case of subspace topology, it was the other way around. That is to say, we had, in the case of subspace topology, I alpha being open, I being open, meant if V is open implies this way, and we put the arrow the other way, V open. Okay, so since I flipped the sides on V, it looks more similar than it should. So we have reversed the arrows. Just a warning, in this case this thing worked, but in general, for example, if the X alphas were not disjoint, you could still take the weakest topology, so that the finest topology, the strongest topology, so that all the inclusion maps are continuous. Okay. However, this will not be the description if they intersect with each other, because these conditions interact with each other. So in general, you have to take a topology generated by these. That is to say, you have to close under open sets, unions, and under finite intersections. So you can always take the sub-basis as being the inverse image sets appropriately, both in the initial and final topology. Sometimes you can take all the sets as that, and sometimes not.